Hello, my name is Shalina Lamb, and this is Lab 4 Oscillations. The purpose of this lab is to analyze the motion of a spring mass system that is oscillating to extract data in order to create a computational model to compare what we observe and what we would expect based on physics principles. Furthermore, this experiment helps us visualize energy and how it changes over time within a system and how that is related to the energy principle. As a result of this lab, the graphs comparing the motion and position of the observed system and the predicted system are very similar with slight variations that we'll discuss later. The computational model also lets us see the total change in energy of the system was zero, which agrees with the energy principle. Before we dive into the experiment, we need to go over the fundamental concepts of physics behind it. First, we have Newton's second law, which states that the change in momentum is proportional to the net force applied. In our experiment, the only forces we are taking into account are gravity force and the spring force, so the net force is just the sum of these. Second, we have the energy principle, which states that the change in energy of a system is equal to the sum of the work done by the surroundings and the thermal energy exchanged with the surroundings. Now is a good time to define the system and surroundings in this lab. Our system will be the mass, spring, and earth, and the surroundings would usually be everything else interacting, such as air resistance. We are assuming in our model that nothing else is interacting, so the surroundings are nothing. Because of this, no work is done by the surroundings, which makes the change in energy equal to zero. In our experiment, we consider the energy from kinetic, gravitational, and the spring, so when we add all those together, that must be zero. Finally, we need the velocity and position update formula for our computational model, which we have previously derived from Newton's second law. So here's the result of what I got in Tracker. The object mass and the strength of the spring were previously given to us. I got the initial position by seeing what the x and y position were when time equaled 0. The initial velocity is just 0 meters per second since it was dropped from rest. The graphs are the result of the position as time goes on. We need to extract some more information from our data before getting to the computational model. In order to find the time, aka the oscillation period, we needed to determine how long it took to go from peak to peak. In my experiment, I used the y position to get the time. The total time it took to complete 6 oscillation periods was 9.117 seconds, which gave an average of 1.52 seconds for each oscillation period. In order to solve for spring stiffness, we rearranged the equation for time period of oscillation to isolate k. Using the time we found for t, we can plug this in, and we got 6.87 newtons over mass for the spring stiffness. Finally, in order to determine the relaxed length of the spring, we manipulated the spring force and the gravity force to equal each other since we're at static equilibrium and plugged in our nodes to get 0.127 meters for the relaxed length of the spring. For our computational model, these lines of code are just our initial conditions that we arranged to fit our system and what we calculated in the previous slides. This part of the computational model, we used the formulas we derived earlier and adjusted it to make sense according to the variables in the code to help compute the spring length and the system's energies. Then, according to the energy principle, the total energy is equal to the sum of the kinetic energy, gravitational potential, and spring potential. This last part of the computational model is just a calculation loop which iterates through each time step for us and gets both the x and y position to show the oscillation, but also calculates how the energy changes over time. I changed the time of the entire loop to run as long as the real model did. Then, I just used the force of gravity, force of spring, and F-net equation, along with the velocity update and position update formulas to help get the position as it oscillates. Since the force here is non-constant, the position update formula uses V final instead of V average to calculate. Finally, the calculation loop was able to get the change in energy during each time step by using the same equations from the previous slide. So here's the result of the observed versus predicted model. The observed is in red and the predicted is in blue. As you can see, the graphs are very similar to each other with little deviations. For the x position on top, it's pretty one-to-one in the beginning, but the predicted model then seems to have larger oscillation periods as time goes on. For the y position on the bottom, it's close at first, but the model seems to go a little further than the observed in the y direction as time goes on. There are a few reasons for possible errors in this experiment. First, our computational model only accounts for gravity and spring force in the net and not things like air resistance, which are present in the observed model. Furthermore, there could be an error since we handpicked the centers of mass. Finally, the oscillation period we used for the model was an average, but there's a chance that some of the oscillation periods in the observed model are shorter or longer, which could explain the deviation with the x position. So, is the energy principle satisfied? Yes. As shown in the graph, the energy change stays at 0 the entire time. Energy is conserved, so nothing is gained or lost. The energy just converts forms between the kinetic, gravitational, and spring, which is why the sum of those will be 0. Finally, we will see the difference in calculating the oscillation period using information from the x position versus the y position. As you can see, there is a difference in the time between oscillation periods when we use the different positions. This is likely because the x position motion is due to the arc motion, while the y position is due to the spring, which makes it faster. Because of this, we would get widely different answers for our time and spring constant, which would lead to different position graphs. For example, if I used the x instead, it might have made my x position graph match more closely to the observed than my y position graph did. Thanks for watching.